Hi everybody, welcome back again. This is example 11.3 and we're going to be comparing the torques that are applied on two different rotating apparati? These two things right here, okay? Question is, which block will hit the ground first? All right, you see what's happening right here. We have some sort of a pulley right here. Right, both the pulleys are the same size. We have a rope attached to them. There's tension applied through the rope right here. Force of tension, call that 1. Force of tension 2, and ultimately that is created by mg, right? But we'll just call that mg, the force of tension. And the question is, which is going to hit the ground first? Because the pulleys are the same, but each of these pulleys has rods attached to them that has masses distributed differently. All right? So it really comes down to which has less moment of inertia, because let's look at 1 right here. We can say the net torque on 1 is going to be the moment of inertia on 1 times the angular acceleration of 1. Which is going to hit the ground first? Well, that's something that is tied in with angular acceleration, right? It's what's going to have the greatest final velocity, you might say, or the least amount of time to the ground. But everything else is being equal. What is different about these two, with the net torque, is going to be the moment of inertia 2 times angular acceleration 2. All right? So which is going to have a greater angular acceleration? Which is going to hit the ground first? All right. If the net torque is the same, so if these are the same right here, we want to find out which is going to have a greater angular acceleration and therefore hit the ground first. So we can really say that moment of inertia 1 times the angular acceleration 1 is going to have to be equal to the moment of inertia 2 times the angular acceleration 2. So which has a greater angular acceleration? Well, it depends on which has a greater moment of inertia. Moment of inertia, I equals mass times radius squared, right? I don't know what I just drew right there. Moment of inertia for 2 equals mass times radius 2 squared right here, which is going to have a greater moment of inertia. Well, this has a greater radius than this does right here. So we can say that moment of inertia 1 is going to be greater than the moment of inertia 2. That being said, we can conclude then that the angular acceleration for 1 is going to be less than the angular acceleration for 2. Everything else is the same, but the distribution of mass right here, even if it's the same mass, but these masses are at a lesser radius than these guys are right here. And so this is going to have a greater moment of inertia than this. So it's going to have a harder time spinning. It's going to have more resistance to rotation than these guys right here. So this guy will hit the ground first. So number 2, I'm so used to writing I's. I tried to write a number and I wrote an I. Number 2 will win, because it will wind up having a greater acceleration, and therefore that mass will hit the ground first. So this is more conceptual than anything else, but it does bring into light the fact that if everything else is equal, the way that mass is distributed is going to change how fast or at what rate your system accelerates. We've already, I believe, illustrated this in class when you look at people like figure skaters or what have you, or in class we've had people sit on a turntable and move their arms outwards, then move them inwards. As you move your arms inwards, all right, you are decreasing your moment of inertia, which is increasing your acceleration, which means you're going to spin faster. Okay, so that's example 11.3, how moment of inertia affects the acceleration of a system. Thanks for following along. I'll see you on the next one.